Hello, I welcome you all. The problem reads, the 10 kg sphere C is released from rest when theta is equal to 0 degrees, and the tension in the spring is 100 newtons. Determine the speed of the sphere at the instant theta is equal to 90 degrees. Neglect the mass of the rod AB and the size of the sphere. So this problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. Right, so we do have some weight in this sphere, okay, and it's W, right, and we are now being asked to determine the speed of the sphere at the instant theta equal to 90 degrees. So we have been told that the sphere was at rest when theta is equal to 0 degrees. Okay, so let's determine these lengths. So I'll call we do have this point, so 90 degrees. So let's use, I'm trying to show the spring at this point. So at this particular point, sorry, let's try and draw this. So initially it is like so. Let me shorten this just a little bit, like so. Alright, so we do have two cases. We have this case at 90, like so, and we do have, at 0, and then we do have this. Okay, alright. So let's call this so at 90 it will be something like this, maybe up to somewhere there, right? I think so. And then we do have this when this system is like this, right? And then we'll have the spring from this point maybe to there, like so. Okay, let's say the spring will be up to there. So let's call this as L1, and we call this as L2, right? So these are the two angles, right? So we are saying L1 is going to be equal to, the length will be equal to 0.3 squared plus 0.4 squared, like so. Okay, therefore L1 is just going to be equal to 0.5. In L2 is just equal to 0.4 plus 0.3. Okay, therefore L2 will just be equal to 0.7. Then we do have L node, which is the unstretched length. Have we been told determine the speed of the sphere, negate the mass of the rod, and so on. Okay, the tension, so it's at rest when theta is equal to 0, tension in the spring is 100 newtons. So they've not given us, but they've given us the tension, all right, at theta equal to 0. Okay, is equal to, so from this, so we've been told at rest when theta is equal to 0 degrees, the tension, let me call this Fs, is equal to 100 newtons. All right, so I'll say let's find the unstretched length L0. So we know that Fs is just equal to Ks, where K is just equal to 500 and S is just equal to L1 minus, this is at at theta equal to 0 degrees minus L0. Okay, and Fs is equal to 100. Therefore, 100 is equal to 500, and then we have L1 minus, and we know what L1 is. So let me write the whole equation here. So Fs is just equal to K L1 minus L0, like so. So we do have 100 equal to 500. L1, we know what L1 is. We calculated what L1 is as 0.5, right? Remember, there it is. So plug it here, we have 0.5 minus L0. Therefore, our L0 will just be equal to, that's 100 divided by 500, and it goes the other side. When it comes, that the other one comes the other side. So this L0 is just 0.3. Okay, so we found what L0 is. Sorry, have we found it? Of course, it's 0.3. So with this, we can now apply the equations of the conservation of energy equation. So say the kinetic energy at point 1, okay, plus the potential energy at point 1 is just equal to the kinetic energy at point 2 plus potential energy at point 2. So T is the kinetic energy and V is the potential energy. So T1 is just going to be equal to, system is at rest, so this is equal to 0. V1G, let's take this as our, we take this as our datum, take this as our datum. So VG1, which is gravitational potential energy, is just equal to 0, right? And then V1E elastic is just half K L1 minus L0 squared. Then we have T2 we do have the kinetic energy, so it will just be like so. And then V2G we have is minus W times H2. And then V2E, we do have also V2E, which is the elastic potential energy is half K L2 minus L0 squared. So let's now plug in all these in our equation like so. Right, I'll not include those that on the non, I'll only include non-zeros. So I do have a half K L1 minus L0 squared, and then I have equals to half mv2 squared minus wh2 plus half K L2 L0 squared. Let's add some numbers to that. 500 L1, we calculated L1 as 0.5 minus L0 0.3 squared. This is equal to half. The mass is just a 10. V2 is what we are looking for, minus W, just a 10 times 9.81. H2 for this ball is with reference to our datum, it is just a 0.3 plus 0.15. Okay, and half 500 0.7 minus 0.3 square. So let's find V2. We can calculate it, right? Yes, we can. Can I move this just a little bit? Alright, like so. So let's calculate that. So we have 0.5 by 500 by 0.2 squared. What do we have? And plus 10 by 9.81 by 0.3 plus 0.15 minus 0.5 by 500 by 0.4 squared. Okay, then divided by 0.5 by 10 and square root of that, we have this 1.68. Okay, let me check it once more again. 0.5 by 500 by 0.5 minus 0.3 squared and plus 10 by 9.81 by 0.3 plus 0.15, then minus 0.5 by 500 by 0.7 minus 0.3 squared divided by 0.5 by 10. Okay, then square root of that, 1.68. So that is finally at the speed of the sphere at the instant theta equal to 90 degrees. Right, so I guess we are done, and I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.